Hello everyone, our team is Team 8. We have a team members Seungmin, Charumi. Because one member left, we are just two members. Let me start our presentation. Our prepared paper is about the estimation of UAVs. Their paper published the IAE Robotics and Automation letter. This paper is about the airspeed estimation of UAV. There is SADS method. This is the method of measuring the existing airspeed. Briefly explain, airspeed is measured using the pitot tube. For predicting airspeed, the conventional method is the same as the above equation. But for various regions, airspeed is easily predicted as below. However, this method has several problems. First, negligibility is sometimes fair. And second, when a over the zero, the term in the root in equation becomes negative. And third, the small angle approximation could induce non-negligible error when UAVs meet several turbulence, which sometimes leads to large alpha values. And the lift coefficient parameters are assumed to be already known, which are usually measured by wind tunnel expression. The pitch axis is it originates at the center of gravity and is directed to the right, parallel to line drawn from wingtip to wingtip. The lower axis is it originates at the center of gravity and is directed forward, parallel to a futuristic reference line. The y-axis has it originates at the center of gravity and is directed toward the bottom of the aircraft, perpendicular to the wings and to futuristic reference line. There are measured by gyro sensor, and it has moment value. The rover is the directional control surface along with the rover-like elevator and aileron that control pitch and load respectively. Elevator are polite control surface, usually at the rear of the aircraft, which control the aircraft orientation by changing the pitching of the aircraft and so also the angle of attack of the wings. Now, aileron are thin flight control surface attached to the trailing edge of the wing of the fixed wing aircraft. Airway is the angle between the blowing wind and the direction of the wing. This is to the angle about the XY plane. SSA is the angle between the blowing wind and the direction of the aircraft. This is to the angle about the XG plane. So in this paper, airspeed is predicted using TCN techniques. Input data are pitch, roll, yaw, rover, elevator, aileron, AOA, and SSA. Their values are pitch curve values. Airspeed is predicted by input data. For simulation, we design the aircraft to the control physical value. It can control all physical values such as pitch and yaw. We predicted airspeed using our new method. Aircraft of simulation is performed by our new method. For simulation, we design the aircraft to control physical value. It can control all physical values such as pitch and yaw. We predict airspeed using the new method, and aircraft of simulation is performed by our proposed method. This is the simulation of the aircraft. We use simulation by Unity. We simulation like this our view method.
For the deep learning model, the official repository of the TCN registered in the GitHub was referenced. Based on this, TCN model design was completed by referring to the baseline paper. This is the result of the baseline experiments. We replicated the original paper and do some experiments. For 3 sequence lengths, we got the result, which is quite similar to the original paper. Meanwhile, based on the model created in this way, 2 more efficient designs were made than before to improve performance. Our first improvement plan is to use better embedding method for input measurement. The original paper just flattened 11 different measurements as time dimension. But on the aspect of the convolution, this method is bad because when convolution corner slides, each position's meaning is going to be different. We changed reshape to just convolution to fix that. Then it is okay to reduce the depth of total network because we need no more such long flattened data. So network depths could be 10 to 6. So it looks like simpler, but we can expect it that it is more powerful. When the model was trained by the same epoch, according to the 2 methods introduced above, it was possible to reduce the loss by about 8% compared to the previous one, especially when the sequence length was small, the loss was reduced by about 12%. At the beginning of the training, the loss bounced unstable, but gradually it converged stably. The standard deviation was reduced, which means that even if there is an error in the sensor, the performance is good. We call that robust at harsh case. We designed a network that shows better performance than before to reduce errors through experiments, especially in harsh cases. On the other hand, the data augmentation result was not attached because there was no performance improvement as expected in the technique, assuming that there was an error in the sensor, such as gyro sensors proposed by Progress presentation. Therefore, if we find logic that can more accurately implement errors in these specific sensors in the future, we can expect to improve performance for domains which lack such data. Since the size of the network has slightly increased compared to the previous one, it is expected that better result will be obtained if we increase the max epoch and train longer. Thank you.